So in the last lecture, I described a variational method for studying quantum systems and how it is useful in situations where you do not have accurate solutions, either exact solutions or obtained by some kind of perturbation theory. And one can study examples of various types. And I also said that the examples where the method has had reasonable success are multi-fermion systems. Multi-boson systems, yes, you can try, but the calculation becomes unmanageable very quickly, and you cannot study large systems. But for fermions, you can do better. So most of the applications and the ones which I'm going to describe today are for many fermion systems. The place which has had good amount of success is actually quantum chemistry, but another equally important area where these methods have been tried is nuclear physics. Because even in the nuclei, the fundamental particles, whatever protons and neutrons, they are fermions, and how they interact and what are the kind of structural properties and energy levels that arise, they are something which are needed in various models of nuclear physics. The problem with nuclear physics is that it is much less quantitative than in case of chemistry, because chemistry, the underlying interaction is just electrodynamics, and we know exactly how the potentials look like. In nuclear physics, the potentials at the fundamental level are also somewhat of a qualitative nature. But yes, people have tried to model nuclear physics system as well. So, yeah. The advantage which I pointed out last time is that even when you have the wave function which is not very accurate, the energy levels have a much better accuracy. So it is useful where your focus is on studying the energy levels and all the related properties which come out of that. But the converse also has to be kept in mind, that just because you got the energy right doesn't tell you that your model is correct. Because the model which describes the wave function can be way off, and still your energy can be accurate. So that is part of the game in many of these quantum chemistry situations. Just because you get the energy close to the whatever the experimental expectation doesn't tell you that the wave function you have modeled is good enough to apply for other properties which are not directly connected to the energy levels. So that's a drawback, but it has to be kept in mind, and people know it, but many times things get ignored. So these are for formulas. Let us start with the basic criterion that you are expanding the possible wave function or a quantum state in a complete set of bases. As long as you have a complete set of bases, any basis choice will do. But what is important for the approximation methods is you want to figure out a choice of basis. That is the purpose of what is the good wave function or good ansatz for the variational techniques, so that the basis set can be truncated. And the more you are able to truncate it, better in terms of numerical efficiency, because your calculation becomes simpler. So that is the game that you are always looking for good choice of basis where you expand and you can keep only a small number of terms and get good answers. So the way it is done in quantum chemistry most of the time is there is something which is called a Hartree basis. What does it do? It constructs the basis as a set of orbital which you can model after, say, the solution known for hydrogen atom. There are angular momentum S, P, D, etc. There are radial quantum numbers n equal to 1, 2, etc. And you take a certain orbitals, a single particle orbitals, and you make a list of them for every atom. And then for a system of atoms, what is the total basis? Well, just a collection of all of them. And as I said, if you are going to look at a complete basis, it is as good as anything else. But the question is what happens when you truncate it? You are going to throw out a whole lot of orbitals, and that's where the accuracy will suffer. Okay. So this is a single set of orbitals evaluated in what is known as a mean field approximation, which means that if you are looking at one particular electron, what is its interaction with the rest of the stuff? Well, you say, I will average over all of them. So the electron moves in an average potential of the whole environment, whatever it is, and that average route structure is mean field. Of course, it is an approximation because there are correlations between when one electron is here, the other one will feel some interaction. It will not be the same as average. There can be fluctuations, and the fluctuations are ignored. And that is the dominant source of error. But yes, it is something which you can do easily because you are only writing single particle set of orbitals. So it gives a starting point. And what you do for going from one particle to many particles is just you use our standard tensor products. One electron has this thing, then tensor product with else, etc. And the way this thing is constructed is completely factorized. And well, the quantum effects will come in, but it will introduce correlations. So it is certainly not something which has the quantum effects built in, but it's a starting point. And the correlations have to be constructed. And how do we add correlations in quantum description? You have many tensor product terms, you construct superposition. Okay. So superposition of many of the tensor products structure, it will have all the kind of correlations, entanglement, whatever you want to bring in. And then the job of the algorithm will be find this coefficient of superposition which we don't know a priori. Okay. So this is the first description which was made, and it was done rather immediately after the formulation of quantum theory was provided by Heisenberg and Schrödinger. Within 1 or 2 years, people figured this thing out, and that is where the original paper by Hartree belongs to. But then something became obvious, and which was added, and that is known as Hartree-Fock basis. And what does it do? Well, it is known that these multi-particle systems, they are all fermions, the wave function is antisymmetric. You don't have a choice. And here it is left as a job for the tensor product to collect all the terms with plus minus sign and do the appropriate superposition, where the Hartree-Fock thing we will build it in. Okay. So this antisymmetry is built in by using the so-called Slater I mentioned this is a characteristic of many fermion system. The total wave function is a fully antisymmetrized version of n factorial terms, but you can write it as nightly as a determinant, and that can be evaluated with order n cube effort for n electrons. So it is complexity wise just a polynomial result, and that is manageable. And it gives basically better answers than starting from just the Hartree answers, because something which is known, you are already putting it in exactly. And again, what are the single particle levels? They will have to be constructed somehow, and then you take the product of n of them, antisymmetrize, etc., and put it in a Hartree-Fock description. So what are the levels? And here there are library packages. They are publicly available in lot of computational libraries and probably these days freely exchanged on internet. Um, and for whole set of low-lying orbitals of simple atoms at least. You can find it, and one of the popular one is given by this name. And which is used, which is an abbreviation for STO, is a Slater type orbital. Three is a number of levels which are kept for every electron, and G is for Gaussian. Of course, you can say I will, instead of 3, I will have 5. Nobody prevents you, but then the space becomes larger, and 3 is kind of used conveniently because people tried all kind of tricks and figured out that it is reasonable result for getting to what I described last time as chemical accuracy. Essentially 1 part in 10 raised to minus 3, you can get there. But note one feature, the wave function which have been inserted here as Gaussians. Okay, we know from atomic physics that hydrogen atom solutions are actually exponentials. And it doesn't matter, Gaussians are convenient for doing many integrals, so that is why it has been dumped into here. But the caveat which I mentioned now becomes very obvious, that just because you got the energy right, you cannot say that the wave function is a Gaussian. Okay, it's just something which works. And if you try to then model the actual wave function as a Gaussian, you will have a very bad fit. It's not the correct description of what is there for the atom. But it works and it is popular. So, yeah. It comes back. And incidentally, the description which I am going to give, there is a good review article you can find on archive. Archive 2111. Of course, it has a lot of stuff, and I'm not going to go through all of that. But yeah, it's a good description of all the things which people have tried. So now let me give a list of approximations which are buried in this description, and which one has to keep in mind if you want to compare the numerical calculation with an actual experimental data, because things have been kind of ignored and they will be there, but what people do is calculate within this approximation some result, and other stuff can be added in some perturbative manner, some corrections if you want at a later stage. So there are, I mean, large number of things. I will just quote some of them. So one of them is a Born-Oppenheimer approximation, which essentially specifies that the dynamics of the nucleus is much slower than the dynamics of the electron. So you can treat the nuclei are essentially fixed. They are not moving, the electrons are moving much faster. And calculate the energy level, and then, well, if the nuclei are then shifted to some other location, you have to recalculate the electron energy in the new configuration. So nuclei move much slower than electrons, and so essentially you assume that they are fixed. So we'll calculate this thing only by giving some coordinates to the nuclei, and then electron solution will be there, and then you change the nuclear position and recalculate the energy, and you have to keep on doing that until you find a configuration where the energy is a minimum. So that becomes a next step in the exercise, that yes, you will find the energy, then you will arrange the nuclear position so that the total energy is the lowest. And that will describe the configuration, which can be then compared to the experiment. It will tell you the lengths of the bonds and the angles between the bonds, and etc. But you have to scan the whole set of nuclear positions before you can do that.
So
Yeah.
that means we will be dealing with wavefunctions, expanding both energy eigenbasis and the position eigenbasis, essentially, because we are changing the position of the nucleus and the energy.
Yeah, so position eigenbasis for the nuclei and energy eigenbasis for the electrons. Okay, that's how the two things are combined. Another thing which is done typically is for atoms, well, there are many electrons. You only look at the valence one, the outermost one. The inner ones are all assumed to be coupled very tightly to the nuclei, and you ignore that. Or rather, what you essentially end up doing is the inner ones screen the nuclear charge, and the valence electron will see a smaller charge effectively, and you just model that. Okay, so you don't consider the dynamics of the inner electron. Then there are a whole bunch of other effects which are measurable, but we are going to cut it out. And they are For example, there are relativistic corrections, nuclear size is not a point-like thing, it is actually finite. There are magnetic moments or dipole-dipole interactions between the electrons. We are going to ignore them, just look at the Coulomb interaction, which is the charge. Then, well, nucleus also have a finite mass, and the way it is included in the hydrogen atom solution is you look at the reduced mass of the electron, because you have to work in some center of mass frame, etc. So all those corrections are there, but they are ignored. Okay, we are only going to look at the Coulomb part, and this thing, well, you will calculate later in some perturbation expansion, add them when it comes to matching the real experimental data. Then the wave function itself, we assume that it is a single Slater determinant to do various calculation. It can be multiplied by this is not the most general solution of an antisymmetric structure. You can have a Slater determinant, but you can multiply it with a completely symmetric wave function, and then the product will still obey the antisymmetry. Okay, so this kind of situation occur in a smaller level where you combine multiple degrees of freedom. Okay, so you can have spin, orbit, some internal they can be organized in many different ways. And one thing which probably you have seen somewhere is when two electrons make a bond, the what you call common or the lower state is generated where the electron spins are antiparallel and the position wave function is symmetric. So the both electrons are in some sense together between the two nuclei. So the total wave function, if you want to write, it's antisymmetry is in the spin, symmetric part is in the orbit or the position coordinate, and it's orbital, whatever. You construct a full wave function, and those kind of effects you have to keep track of. Okay, if they are not properly kept, well, you include enough labels, and many condensed matter applications actually use these kind of labels explicitly to figure out where the antisymmetry of the wave function is, and it can be any mixture of various kind of labels which may be present. You have to keep track of that as well. And then, yeah. Tensor? it's just a wave function of many particle states. You can write it as a tensor product, but then it will be a huge expansion. But like last time what I said, that an antisymmetric wave function can be written as a determinant, but I can also write it as a determinant times a permanent. Nothing goes wrong. And that permanent part is kind of left out. Okay. Then truncation is already something which is there. We already described it. And you have to, well, keep track of how good the truncation is. And the only way to figure out is add one more term and see whether your answer gets any better or not. Nothing more sophisticated than that, but you have to still check that yes. And one more thing, that there are certain kind of Coulomb corrections which are not part of this antisymmetric statistics. Okay. And this exists, they mostly come out of fluctuations. And we have thrown out the fluctuations. So this is something beyond the mean field description, which is used to calculate this orbitals, and yes, those things will be lost, and they have to be included. And a common example of this phenomenon is something which is instantaneous. Van der Waals interaction. So these are fluctuations. They are things which are observed and sometimes needed to describe the material properties properly. The interaction is much weaker than the Coulomb scale, and the way it is understood is that they are perturbations or fluctuations in the charge distribution. So when you put up one position of an electron, it can be interpreted as a dipole because the charge is moving, and that creates a consequence in the other one, that the other side also the dipole will readjust. And it is basically instantaneous. When this fluctuation happens, the other fluctuation will be the result, and then it can go back. So these are things, but when you talk about this van der Waals interaction, you are going beyond mean field. In mean field, you are not paying any attention to the fluctuations whatsoever. And so these are the things which are also there, and well, you can say that I will add it afterwards. So these are all the caveats, but you have to keep in mind when ultimately the time comes that you got some result and you want to match it to the experiment. Well, not so quickly. You have to see how much other stuff has to be taken care of in the middle. Okay. So now I can write down the model which we are going to work with. Yeah.
What does the new field effect has an effect on the electrons, if not for fluctuations? And what does it do to the electrons?
Mean field description is that you want to study one particle, you take average over the whole environment. The environment is considered fixed. This doesn't fluctuate. Okay. So if there are fluctuations of environment, yes, your degree of freedom will also going to get perturbed. And those are the kind of dipole-dipole effects which occur. They are not part of the mean field. It's a leading correction is the dipole-dipole. Of course, you can have more complicated disturbances and they will have their own description. Okay. So now I can write down this fundamental Hamiltonian, which we are going to deal with all this approximation, and it has 3 parts. One of them is kinetic energy, which is h cross square by 2m times the Laplacian. The other term is interaction with nuclei, which is the Coulomb force. Between electron at position I and a nucleus at position K. And Z is the charge for the nucleus. It can be a screened charge if you are looking at a valence electron only, whatever it is. And then there is a repulsion between electrons. And I think, yeah, if you can write it in 2 different ways, either I greater than j, then there is no multiplicative factor, but if I write I not equal to j, I should put a half, because double counting occurs. I and j are kind of interchangeable. So this is all there is, because the electrodynamics tells you that these are just available interactions. There is nothing more than that. In particular, this is one body term. Nuclei are kept fixed. This is also a one body term, and this is a 2 body interaction. Nothing at a higher level. So these are single particle, and this is 2 particle. And we know everything other than the locations of the electrons. Nuclei are kept fixed. I want to find the wave function which will minimize this energy. That is just a variational problem now. Of course, now I have to find some good basis set to expand the eigenstate of this, and that is where all these STO, 3G kind of stuff comes in, what they are, but the Hamiltonian is fairly clean definition. Okay? Nothing more complicated than, as I said, if you go to nuclear physics, then even this becomes quite messy. So that is a different story. But yeah, people have tried applying this logic to nuclear physics interaction as well.
So there should be Dirac square.
Hmm?
Dirac square should be
Oh, I should write the Laplacian, so it is L square. Laplacian sometimes is a triangle. I wrote a gradient, so yes. And now means you assume that some basis set of wave functions, which I will just call some state phi I. It's a generic. Yeah, it's not the same I, so it's some set of I, whatever it is, which will be written as some tensor product description with a whole lot of terms, etc., etc. So now, given this Hamiltonian, what is done? The first step is calculate all kind of matrix elements, and even when the problem is put on a quantum computer, that part is still evaluated classically. And those are just what you call one particle and two particle matrix elements. So one particle matrix elements are fairly simple. These are expectation value of the Hamiltonian, the kinetic energy part, plus the electron nuclear part between one particle states I and j. Of course, the total wave function has many different coordinates, but when you say I will look at only terms which are single particle objects over here, all the other terms just multiply and become diagonal, giving identity. All those indices are equal. Only the I, which belongs to the particular label which you are looking at, that one particle, that will survive. And this can be now written in terms of, well, some notation doesn't matter very much, but I can write it still in the same language. The sum integral minus h cross square by 2m. Then I have to put the, okay, wave function first. So otherwise, is the integral over the position, whatever it is. I'm not going to write it explicitly, but there is a phi I star. Then there is this gradient. Then there is a e square Okay, I have to give it a label. Okay, so let me call this thing as a H I J. And it depends on the one particle phi I star and another particle phi j. Wave function, what has to be kept in mind that there are two indices over here. The reason for doing that is the wave function which we picked up by any of this Slater, orbital and Gaussian, they are not necessarily going to be orthogonal. Okay, if it is orthogonal, they will be completely a diagonal matrix, but it may not be. We are just choosing some basis, and that's why this matrix is little more general, that you have to keep track of it. But all of them are dependent on only one particular electron. I is a basis label. And then to take care of this stuff, you need a 4-index object, which is a phi p, phi q, and then this is the electron part of the interaction, and phi r and phi s. This one thing which has to be kept in mind, that the orders of these wave functions matter. The reason is the antisymmetry which we have built in. So when you do the calculation, you have to make sure that you maintain the order, otherwise you will get a wrong sign. Okay. So what I mean, I put some PQRS, but what is the label here? There is some sequence, and you have to keep track of it. And this will be now a double integral x1 and x2, and it will have phi p star x1 phi q star x2 times this e square of these indices, it is r1 minus r2. Let me call this r1, r2, these are the positions, phi r, r. I just picked one particular convention where this thing is a transpose of it, so R2 of this is connected with R2 of the first term here, etc. But whatever it is, you have to stick with one particular convention, and I have assumed a particular convention here. And now you do the necessary calculation. These numbers are calculated a priori by using some of these whatever sets of wave function, and these are known integrals which you can perform in advance. So this whatever Hij, H, P, Q, R, S are evaluated at high accuracy classically. And so what is the remaining job for the variational part is to write the Hamiltonian, and there are two languages again historically called first quantized and second quantized version. So this first quantized version just looks like bunch of projection operator with this matrix element. So there is a sum over I, sum I should not confuse this ij over here, so let me put some other label mn. And then there is HMN, I. Something like this, which stands that this is the contribution to the Hamiltonian of ith electron. It can be given by this matrix element between level m and level n with this particular coefficient. And then there is a second term which will have now more complicated labels. Let me get the order which is used correctly. I, J, and R and S. Okay. So this is I not equal to J, and then there is a half, and then there is a phi I P phi J Q. That's the label. Yeah, so these are just in some sense the projection operators for these particular components, and the strength of the interaction is this coefficient which have been evaluated, and that makes up the total Hamiltonian. And this is a language where you are explicitly keeping the wave functions of the states around in the label, and it's completely legitimate to do calculation with this, and nothing wrong with it, but it's somewhat more convenient to use a language which is called second quantized, and the nomenclature, well, again, invented by Dirac to describe the structure. And the difference is that here the wave functions are treated as some complex variables, and in the second quantized version you make those states also field operators. They are not functions, but they become operator, and then you define whether the state is present or absent by saying that it is occupied or unoccupied. So it's an equivalent language. Probably you have seen both of these language while dealing with harmonic oscillator, where you can write the Laplacian and the potential in one case, and Another case, you will just write A dagger and A. This one-to-one correspondence, both are the equivalent, but it's easier to put in these things here. So this extra label basically goes away. So this is wave functions. And here there are creation, annihilation operators. And probably the way I have written is coefficients, H, P, Q, R, S. And I think there is a half which is also probably kept here from normalization. Yeah. So the second quantized version turns out to be more convenient in representing with bits, because we are dealing with fermions. The occupation is either present or absent. There is no double occupancy or thing like that available. So you can just map it into 0 and 1. So this creation and annihilation operators have only eigenvalues 0 and 1. You can call them bits, and then you can work in these particular labels to see what are the coefficients which I need to find a superposition of many occupied, unoccupied levels, some kind of a mixture. Okay. So that is well, the kind of all the background which is needed. Yeah.
Can you explain the order of which you have?
This.
Is it not 5D R2, 5D R1?
You have to pick a convention. Okay, the way this notation is written is this is a transpose of that. That is why I wrote it in the particular order.
When we transpose, tensor does not change the order.
Yeah, the transpose means AB, the whole thing transpose is B transpose, A transpose. You have to treat them as operators, yeah.
But this is tensor, that is tensor order.
Yeah, it is still a tensor index, yes.
Tensor will not change the order.
No, it does. If you have a matrix Aij, the transpose will become Aji.
So this label cat phi r phi s is this product, not tensor product?
It's actually a subset of this whole wave function. The only thing is there are all kind of indices, and the ones which don't appear inside here, they got integrated out. So this is the only part of the wave function which remained, and for that I calculate the matrix element. But it's a much larger number. If you have n particles, there will be n different indices, and then what you are doing is you are tracing over n minus 2 of them. And these two are the ones which remained because there was this extra Hamiltonian acting on them.
And this picture does not include the Coulomb interaction set, right? Only the mean field part is considered.
only this interaction. It's all static. Position at some particular time given for every electron, and I'm calculating the energy. Okay, so yeah, that mean, compared to the real world, there are a whole lot of approximations which have gone in. That's why I wrote down the list to just give an idea. We're ignoring everything, just calculating this particular part, which is in some sense the dominant part, and then everything else will be corrected a little bit when needed.
So these are all calculated at a particular snapshot. A particular instant.
Yeah, so because this is all time independent, it is like a fixed instantaneous description, nothing there. No dynamical stuff is there. They have to be added everything after that if you want to correct it. And now if you can count it, how many of the terms will be there? Well, if I and j go over, say, and labels, so let me write down that. This is a generic feature, so suppose I have n electrons. That means there will be some order and basis labels depending on how many terms I keep in the orbital. In this particular case, there were 3. But something of that thing is there, and then the terms over here, this H has order n to the power 4 elements. Because they're dealing with indices going up to 4 different values. And this is now built in. Can't simplify it any further. Now I'm come back to the question of how are you going to realize these operators in the computer. Okay. So these are various operators. So I have to find something which obeys the corresponding rules, and then this so-called Pauli basis is convenient, which basically went like any of the polymetrices going from various labels of sigma, either identity or 1, 2, and 3 for the non-trivial Polymatrices, the important part which is useful, that this is orthonormal. It has a what you call anti-commutation relations are kind of built in. And the third thing is Hermitian operators have real coefficients. So if you are expanding any of this Hamiltonian kind of thing in the Pauli basis, this is already Hermitian, and so the coefficients are all real. You don't have to deal with complex numbers. And anti-commutation rules are useful for the reason that this creation and annihilation operators, they belong to fermions, and we need this kind of various things. They are creation and annihilation operators, but they have to obey this algebra. So agar and A will give you a Kronecker delta, and these brackets here are for the anti-commutator, and if both of them are creation or both of them annihilation operators, they anti-commute, which kind of guarantees that there is no double occupancy. If you act on twice, it becomes 0. So we have to find a physical realization of this, and that also this Pauli structure helps, because we can arrange some anti-commutativity appropriately to do this particular job. So I will give the simplest construction, which gives, it is not necessarily the optimal choice, but where all the properties are nicely put together, and that construction goes by the name of Jordan-Wigner choice. A particular labeling scheme which follows this label. So where we have to take a convention. 0 is unoccupied. Well, that is standard. It's not necessarily in this. And 1 is occupied. And then you have a 2-component qubit. The upper one is 0 and the lower one is 1 in the standard notation. And you can construct this erasing and overing operator just for the 1 qubit. Okay. So single qubit, you can map AI dagger to, it will take 0 to 1 So the matrix will look like, I think it's 1, 0. These matrices are not Hermitian, okay? A dagger and A. This thing is Hermitian, whatever, Hamiltonian is that. So this will take 0 to 1, so it is a creation operator. And this you can write it as a half of x, I just label I, and minus I times yi. But this is a Pauli notation, okay? I'm choosing x, y, z instead of sigma 1, sigma 2, sigma 3, but that is understood. And this is the complex conjugate. So this will describe this commutation rule at a single point correctly. So that is guaranteed by the anti-commutation property of x and y. But I need more than that. And why? Because this is a multi-qubit system which I want to describe. And if I just take tensor product of this, then individual factors will commute. But I have to make creation operator at one site anti-commute with creation operator at other site. And just tensor product is not enough. But there is a simple enough solution to that particular problem. It's a easy trick. That extra commutation, so AI dagger will have this stuff, x I minus I y I multiplied with all z without whatever stuff is inside here. Okay. And the same thing. This is the whole Hilbert space. So look at what this thing does. It's adding all these z factors which will commute with each other. Okay. But if you take this I and let me call this j, okay, just to avoid confusion. It doesn't go to, okay, j, this is wrong, this is it's a partial things. It goes up to I minus 1 and this will go up to j minus 1. Okay. So this one has this xi minus yi in ith location, this one has this in the jth location, and you are multiplying with this other Pauli matrices at different locations. Now in this notation, this z's etc. At different locations, they all commute. But what happens when I and j are in the same index, then all this other stuff will get paired up and doesn't do anything, and you get these relations. But when they are not equal, one of them which is in a slightly displaced position compared to this. So there is a string of this I minus 1 and then this is at the location, and this one goes a string at the j location, and there is a location where this string terminates, and beyond that it's identity. So that I'm not writing the identity part here, but if you want, you can say tensor of identity from I plus 1 to I n, and the same thing here, identity of j plus 1 to n. So one of them is a longer string than the other, and when you try commutation, the z will anti-commute with x and y both. So the sign will flip. So these are now represented as a string of this Pauli matrices. String starts with all the z until you reach the location, and there you put x minus iy or x plus iy. And that solves the full algebra statistics of this creation and annihilation operator. And now this becomes the construction, and then the Hamiltonian is of this particular form. So you have to do all the multiplication and various terms, etc., etc. But now you have a scheme to implement this Hamiltonian, and then all you are doing at the end of it is calculate the expectation value of a particular wave function of this particular Hamiltonian, and that means you have to measure the expectation value of the Pauli matrices. It's already in a qubit notation, and you know how to do that in a principle. Of course, doing it in a actual code, you have to keep track of all the indices and sum over all the possibilities, etc. But it can be done. The calculation will have the complexity which is order n raised to 4. So that is the space in which all these matrices are working. Now this is the simplest choice which can be understood very easily as a solution to this anti-commutation problem. But there are other solutions, and I will deal with them next time. But before that, I want to give some explanation of how this structure has to be used. Okay. So we need more ideas about completing the problem, because the problem was not to just calculate the energy expectation value. The problem was to find a solution which minimizes the energy. Okay. And this is fine, but it doesn't tell you where are the variational parameters. There are none as far as this formulation is concerned. You put some fixed Hamiltonian, you wrote some wave function taken from some basis and put some numbers, but everything is constant. This is some constant evaluated. This is some representation which is also fixed. So you have to now bring in the idea of what are you going to vary to get this particular problem completed. Okay. So the variational problem is solved in a hybrid manner. So one step is choose specific superposition I wrote this generic state, something, but you start somewhere by putting some superposition coefficient. It might be very simple that it will be just 1 in one state and everything 0, and then the other one similarly to simplify the matter, but you have to start somewhere. Then evaluate this expectation value. It can be done in a quantum method with all this creation, annihilation operator, whatever you want to put, and you can measure some expectation value at the end. Then comes the variation coefficient. Then you have to take another configuration, probably nearby. If you don't want to make large changes, calculate it again. And find the gradients of this particular expectation value to see if there is some direction in which it can decrease. And this is done classically to evaluate the gradient after perturbing the parameters, and then you keep on doing the iteration. In some sense, there is a quantum step and a classical step. They alternate till you reach the minimum. So this is a more global prescription Well, you can ask how many iterations it will take. It's not very clear. It will depend on the technicalities of the problem and how good was the initial point. Well, if you're far away, maybe it will take many steps to reach the point. But you can ask that how will I implement this perturbation? Okay. So basically change of the superposition, so coefficients. So there are now labels. So the idea which has been successful is to use Hamiltonian evaluation to change the coefficients of the perturbation expansion, where what you can write is this set I prime is equal to e raised to and why such a prescription is used, putting some operator in the exponent, and the reason is it has some nice properties in terms of the quantities which are conserved. We just put a arbitrary coefficients as some power series, the normalizations will not be nicely conserved. This structure preserves those relations kind of exactly, and this is known as a coupled cluster it can't be called theory, it is just a method. And what this operator T has to contain? Well, you are only very simple methods for changing the coefficient, which said that for every electron there were some set of basis labels, and superposition will only consist about the electron going down and up between the set of whatever its basis state is. In that STO3G there were only 3 possibilities. So what you want to do is let the electron move around on those 3 orbitals, and how will it do that? Well, it has these excitation terms which will have very simple form. Again, a bilinear in terms of creation and annihilation operator. It will take an electron from level Q and put it in level P, the transition. So these are the same Pauli algebra operators which you can use. You have a prescription of how to include them, and then you can put those terms inside this operator. This A is a that's a variational parameter to be optimized, because you are shifting some of it. How much you want to shift? Well, depends on the particular problem, how much of the two levels should be superposed to get a good solution. But you hope that you start with a good approximation. If that is the case, then this perturbation will be small. And then this so-called Hamiltonian evolution with this operator will converge reasonably quickly. So, means arrange this A to be small and this is the same problem in the Hamiltonian evaluation. Is some operator is given, you want to exponentiate it. It's written in this particular basis, but you figure out how to deal with that. The sizes are not going to be very large because our spaces, whatever they are very finite, but you still have to do that particular job. And then what changes in case of a quantum case? This has been part of the machinery which people have been using for quantum chemistry for 50 years or something like that, before they started talking about quantum algorithm. So, what you need is not these operators, but it's what is used is called a unitary coupled cluster method. And it modifies this particular operator. And that is what people have tried. And that structure is the operator, which is slightly different from this, and the way it is chosen, this is strictly unitary matrix, because T minus T dagger is anti-Hermitian. So when you do this, of course, the unitary thing is a much stronger constraint that the norm of the state will be preserved. When you apply this particular transformation, it is still something which you can do with the Hamiltonian evolution, no problem at all. It's exponential of a matrix. This structure of T will be just this, but you are just combining two of them together and evaluating it and hoping that your initial A was not too far from whatever you want to go, and it will converge in a few steps to whatever you want to do. And then still there are techniques left that yes, you have to exponentiate it. It's a many particle system, and how will you arrange the various terms? There are techniques. I will talk about it next time. But this is the whole organization of the problem. It's not trivial, but people have done simple simulations for basically diatomic and triatomic molecules. Okay, not very big, and there are papers you will find in the last few years which have evaluated all these quantum algebra on one of those machines by IBM or Google, etc. they have, and they have claimed to have reached a chemical accuracy with the whatever simulators they are available. So that is roughly the status of the field. I have still to describe more techniques on top of it. I will do that next time.